the composition of two or more rigid motions is a rigid motion. So basically we do that for like one transformation. For example, if we took like a triangle and translated it down and right. Okay, that's a rigid motion, congruent shape. The pre-image and image are congruent. But suppose we did two transformations. Let's just make it easy. Maybe I translated it first right, and then I translate it down and have two shapes. Well, if you do more than one, then the final shape will be congruent as well. That one might be kind of an obvious one. You do any number of rigid motions, the congruent shapes, the final one will be as well. I kind of said that here. Okay, so there's two important theorems from this that I want to talk about. First one, I'm going to ask a question first. So I have the letter E here and the letter E there. Copied this one, pasted it over there. Now, one option is I could do a single translation. Right, just move it to the right. We're not on a grid. We could be, but we're not. So just moving it right, whatever amount, so that matches up. The question is this: doing only rotations, okay, composition of rotations, which means you need more than one. Oh, reflections. Gosh, I'm so silly. Reflections. Using only reflections, what is another way that I could get from this E over to there? I want you to think about it for 20 seconds. So think about it. Again, the question is, using only reflections, how could I get from this pre-image to that image? Only reflections. So, thoughts? You can only do reflections. How could you get to from this pre-image to that image? Sarah?
Reflect it twice. You have two lines and you reflect it over each line.
So, like, you want to reflect maybe like across this line, and then, well, that wouldn't match up exactly. Or what lines are you talking about?
Like vertical? Horizontal?
And yes, and the main characteristic is they're going to have to be parallel.
Yeah.
So you can just do two random lines. Yeah, very nice. So it could actually be, the first line could be any line, any vertical. In a second, I'll generalize it. So it doesn't have to be always a vertical line. But for this one, it does. So you could do any line to start with, any vertical line, actually. So how about I just do one that's close to it? And then it'll be roughly here. All right, like that. And then the next one, so you reflect again, vertical line. This time it's got to be really at the midpoint of these two shapes. So it's got to be, really right there. And so then when you reflect it this time, it'll be back there. Very good. So overall, I'm going to sum it up in this theorem. But if you reflect over two lines and they have to be parallel, then it's equivalent to doing a single translation. So let's just go ahead and read that there, and then I want to say something else about this. So a composition of reflections across two parallel lines is a translation. So basically I did two reflections, the lines have to be parallel, and it will form what's equivalent to just simply translating from the pre-image to the image. All right, so a couple of thoughts about this. The first line could have been anywhere. It could have been here. It could have been here, actually. Right, and then from the midpoint of these two, reflect over, get there. It could have been here, so that then it's like this, and then the second one is in the middle, and it flips over itself. All right, so the first one is any vertical, and the second one you got to find the middle of the two, the letters. And that one, and that one. The second thing is this. Let's see, so we did one reflection, got there, two reflections, got there. If we did a third reflection somewhere, so I do it here, it'd be back to that shape, and a fourth reflection would be back to this one, and a fifth reflection there, and a sixth reflection like that. So there's a pattern. If you do an odd number of reflections, 1, 3, 5, the shape would be a single reflection. And if you do an even number of reflections, it's equivalent to doing a single translation because the shape is back to the correct orientation. So that's actually an extension of this theorem. Even number, you get, what did I say, a translation. Odd number, you get a reflection. Any thoughts on that? Very nice. Let's do, I just want to show you one other one. So this one, it's just, I just want to show you that it works if the lines aren't necessarily vertical. So let's reflect this letter J over line M. And then the result, we'll reflect it over M. So I'm going to reflect it over M to start. This one. So that was pretty good, right? Tough up here. If I were you, I'd just turn the page and you could probably draw it a little bit easier.
Wow.
It's going for a candy cane. Got some. Yeah. So then I'm going to reflect that one over line N. And let's see, it should be, yeah. If you line it up, it should be back like that. Yeah. So again, reflect, you can turn your paper a little bit, might look better on yours. So, okay. And now, so what it shows, it's a single translation from this J down to there. That's the first theorem. Ready to move on to the second one?
Yeah.
Yeah?
Yeah.
Oh, okay.
I said heck yeah.
Sorry. So the second one is this. Here, look at the triangles first. Let's actually just do this one. So this time I'm going to reflect around intersecting lines. So I'll start with the triangle, and I'm going to reflect it over line N. That's pretty good. Roughly like that. Or not N, A. So I reflect it over line A. Looks roughly like that. Now let's reflect again over line B. Well, that's a little off. Something like that. Now, it might be hard to tell on this one, but really this side matches up there. You can't tell. And this side is here. And then these two sides go together. So if I don't put that down, it might look like a reflection on this one. However, so if you rotate around two intersecting lines, what was it actually? What transformation? A translation, reflection, rotation, or dilation? Yeah? Rotation, single rotation. So this has been rotated around like that. The angle will depend on the lines. Angle depends on the lines. So at least we can say it's a rotation. Okay. So I summed it up right above here. A composition of reflections across two intersecting lines is a single rotation. So the first one up here, two parallel lines, you get a single translation. Two intersecting lines, you get a single rotation. Okay. Let's do it with the letter R. I think this one, once I reflect both times, you'll clearly be able to see how it's been rotated, if I can draw it well. So let's reflect that letter over line B. So it would be roughly. That wasn't great, but I'm going to keep it. It's hard up here. Then I'm going to reflect over A. Okay, my size is getting a little bit off, but it'll be roughly like that. And so hopefully if you just, disregard this one for a second, just think about here to here. By the way, we're rotating around this intersection point, by the way. So, right, you see how it's been rotated around there. This is now up there, and this is now down here, rotated. So those are the two related theorems that I want you to know. Reflect over parallel lines, translation, and reflect over intersecting lines is a rotation. Anything else I can answer on that? Those are just two little fun theorems. Flip it over to the back. Last thing I want to do, so this, as you're flipping over, I'll say one more thing about this. This was a topic, it was on the standards, then they said, well no, we're going to take it off, and they switched to OST, now it's kind of back on. I don't know what they would ask question-wise on this, except possibly like just simply the theorem. You know, what a composition of two reflections over parallel lines is a blank, and you have to say translation. So that's what I can think of. The back two I just wanted to talk about for a minute. These are actually non-standards, so they're not on there, but it's tough for me to talk about transformations without saying something about tessellations. So these are examples of tessellations. You start with a shape, and you just repeat the pattern. And the rules are you have to fill the space. There's no gaps, and so no overlap and no gap. Oh yeah, I was gonna say basically no overlap and no gaps. So it's not going to work with every shape. They were like circles. You couldn't fill the whole space. You can make a pattern with circles, but it won't fill the whole space. But I just found these two. You could Google this, and there's a ton. I thought this one was nice with the arrows and then the backwards arrows making it fit. Here's another one. There are properties for these, and I haven't done too much with tessellation, but there's properties on like forming them, and how if you have this angle, there's properties once you look into these, but we're not going to talk about those. Those are not on the standards. This one's kind of a cube-like one, squares and cubes. Do you know what I thought of earlier with this one? Anybody know the game Cuber?
No.
Yeah.
Are you talking about the one where you kept tracking it?
Yeah, like he's like here and you like jump up and like
Yeah.
jump up and down. I don't remember what you're trying to do.
Trying to light up all the squares without dying.
Yes, light up this. Yes. What's chasing you on that game?
Or like rampant spiders.
The
and
geometry
stuff.
monster.
You play that game? Yeah. Yeah. Well, that's what I thought of. I just randomly thought of it earlier. It's like that is exactly the board for it. One other thought about tessellations. Did anybody do this a couple years ago, like tessellations? Have you done them before?
No.
Too much. So your teacher, I remember when I was, I don't know what grade, but my teacher gave us like squares, and you had like I don't know, like 20 sets of squares, and you were supposed to cut it out. And so you cut out a certain shape. So like I cut out something like this. And then you put, so I cut this part out. And then you put the result over here. That was the right way to finish up.
Well, I do something like that in our class all the time.
And so then the result is, let's see if I can do it. You did it in art class?
Yeah, imagine I did the lizards.
Or it'd be better if like graphic computer design or something. So it's supposed to fit there, and it would if you cut it out perfectly. And
Whoa.
okay, so I didn't make it perfectly.
No.
But you just take like a square, and then you can tessellate and fill up the entire space. It could be fun. Okay. Last thing. Any thoughts on tessellations?
No.
They're fun, but not much else we're going to do with them. I have a little mini golf application. I've done more with this in the past, but it's just a fun little thing. Basically, if I was actually completely doing this, we would need to know constructions already, which we're doing next. And you need a compass and a straight edge. And what you can do is you can figure out how to get a hole in one on any hole. any golf hole. This is assuming there's no, well, yeah, I was gonna say slopes, yeah, hills or anything like that. I have a lot more complicated drawings too, bridges and stuff, but basically it's this. It's all boils down to reflections. You take, here's the ball, here's the hole. You want to go here, and what you do is you choose a wall that you want to bounce off of. So if I want to do it in one shot, I choose this wall. If I want to do it in 2 shots, maybe I could choose this wall and then this one. You could do both.
Do 2 shots.
I can do 2 shots with this one and this one as well. Yeah. There's that.
Well, no, I mean like you can do 1 shot with the second wall.
Oh yeah, you can.
But yeah, you're right. I could do 1 shot, one here as well. So let's just say I want to bounce it off this wall. I'd have to do a compass construction. And we'll talk about that next year. And I would reflect this point over this line. And so it'd be somewhere over here. And then all you do is you aim. You aim at that point. And the angle here would be the same as the angle up there. And so then it goes, then you bounce off and go directly there.
Wait, can you say it again? Oh. Yeah, can you say it?
Yeah, the process you would,
Yeah.
and this is what I do in mini golf. Don't you like I like reflect over
like
that. Then I gotta hit that point, you know.
No, that's what you do.
Yeah, I grab my compass out and I just tell the person I'm playing, like, give me a second. And I use the compass and
it's vision.
Yeah.
Give me a minute, let me figure it out. Okay, so yeah, so whatever the hole is, you choose the wall you want to bank off of. I choose that one. So I got to reflect this hole, that point, over that line. So reflection, it would be somewhere up there.
Oh.
Okay, thanks.
Somewhere up there.
Now I know how to cheat.
And then you shoot exactly where that would go along that path. But it would, of course, hit the wall and then go in. Assuming you have the right,
Well, how do you figure out which angle?
Could you get like chalk when you're playing mini
Philosophy.
golf and do this? Like draw it out.
perhaps you
Get
could.
some tape.
What, Madison, did you say?
How did you get that angle that goes into the hole?
How did I what?
Get the angle that goes into the hole.
It just works out as long as you reflect over this line. It will be the right angle of incidence and the angle of, what do they call it? Angle of reflection. So the angle it hits the wall at, it will bounce off in the correct angle of reflection. Now, if you want to bank off of 2 walls, I think then you have to, let's say I want to go off this wall. I have to reflect this point over this line. And then I could aim right here, and it would bounce off of that and go up there. Well, I don't think it would do that. It'd bounce off of that. Oh, I know. It'd bounce off of that and go up there and then down in there.
Oh, wait.
Wow.
Couldn't you, like, reflect that one? Can you reflect the hole over that purple line over there and then find a shot where you can get it into the purple, get it into the hole from that purple line?
Just one off? Yeah.
Yeah.
Yeah, you could just reflect this point, you know, here. Oh, no, I'm sorry. This hole would be like here. And then it'd be something like that.
Oh, okay, yeah.
Alright, isn't that fun? Well, we need to actually do that. I would need to teach construction, so we might come back to it if there's time during constructions or at the end of the year. That's kind of fun. Actually, it's all based on congruent triangles. That's all for today. Any thoughts, questions?